So I won't be talking about quantum mechanics, I'm sorry. We're back to galaxies, and I'm going to talk about the evolution of small galaxy population. This work is thanks to a cast of thousands, both people working at the University of Washington in the M-Body shop, current and former graduate students. I want to particularly point out Lauren and Michael. A lot of their work I'm going to be presenting, and also people at the Parallel Programming Laboratory at UIUC who helped us scale on blue waters. Here's an outline of my talk, going through, well, annotated with some of the points that organizers wanted us to cover. Since I have this slide up, I want to particularly point out the help that I got from the Blue Water staff. The help desk was amazing. Gangbin and Celso were great. The people that found the that DRAM rowhammer bug, I was flabbergasted that they were able to figure that out. So kudos to the people working at Blue Waters. So why it matters. So what we're trying to do in galaxy formation is to take this picture of the universe, which is a snapshot of the cosmic microwave background when the universe was only 380,000 years. That's a few nanoseconds old. And take these fluctuations. And this is also 14 gigaparsecs on a side, and I'm going to say, all right, let's take a little volume of that. Will that collapse into something that looks like this? And now the length scale is 10 kiloparsecs, so a factor of 1,000,000. ChaNGa did a wonderful job of pointing out how resolution matters in order to form something like this, and Brian also summarized it nicely. So let me just make an exclamation point on the fact that what you're seeing here is not the dark matter, which dominates the gravity, it's the baryons, and the baryons matter. Okay? Some of my best friends are baryons, okay? And so the baryons you see here are some gas and some stars, and the perhaps not obvious point is the dynamics of the baryons also influences the dark matter. So if you're going to make statements about what the dark matter is, which is sort of the holy grail of these kinds of simulations, we don't know what it is, what can we say about it, you need to understand what the baryons are doing. Because the baryons, for example, if they concentrate, the dark matter will also concentrate around them. A rather surprising result is that if there are violent motions among the baryons, supernovae and things like that going on, that stirring motion can also stir the dark matter and actually smooth out dark matter distributions. But understanding baryons means understanding star formation. And star formation is this multi-physics, multi-scale problem. The differential rotation in those spiral arms is driving turbulence. There's also turbulence being driven at the sub-parsec scales. And this is, well, Brian is getting there, but essentially unresolvable in these cosmological simulations. So, you know, just a picture for scale. Notice scaled here, 4 parsecs. This is a picture in molecular gas of a nearby star-forming region. The colors are velocity channels, just showing you both the spatial and velocity structure that you would have to model. And doing that in a cosmological simulation is still beyond what we can do. So what do? Well, we still need to shoot for resolution. We need a large enough volume that we can capture the torques that spin up our galaxy and make that lovely spiral structure. We do adapt to the galaxy scales. Brian uses AMR. We use an SPH Lagrangian method to do that. but we have to work hard on capturing this star formation still as a subgrid model. We still need the sort of molecular cloud scale, that's 100 parsec or so resolution to get down to a molecular cloud, but at that scale, we have a model where we allow the stars to form in high density environments. We have a model that injects that supernova energy that you've seen in other talks into the interstellar medium, and there are issues with limited resolution that we have to mitigate as well. But we try to do this on models of present-day galaxies, and there are scaling relations that we can match up. And we have a Kriging technique to tune all these parameters to match up stellar populations at the current day. So that's the physics we're trying to model. The actual observations we're trying to address are current observations and near future observations from the Hubble Space Telescope. So Brian showed you a picture of the Hubble Date Field. Those observations are covering roughly a 25 megaparsec cube volume back at a redshift of 4, which that's early in the universe histories. And so it's that population of galaxies that we want to model so that we can understand their physical properties, and so that we can make connections of what those galaxies are like to galaxies today. Our resolution studies indicate if you want to understand the morphology, the detailed disk, bulge structure, you do need a few million particles per galaxy. And so that instantly sets the size of a simulation we need to do, and essentially it's of such a size it only fits in blue waters. Now the issue is dealing with a large system with blue waters, and I want to make a comment here, which this particular item from the blogosphere has not been mentioned at this conference yet, so I thought I'd bring it up. So the point of this article by Jonathan Dursey, some of the points actually were addressed by Scott, the guy from Cray last night. Steve Scott, thank you. But one of the points I'd like to emphasize that he makes here is that MPI, he makes the argument that the MPI is sort of the wrong level of abstraction for programming a large supercomputer. For example, you know, an MPI send to a particular processor, that sounds an awful lot like move result to register B, right? We're essentially assembly level programming our supercomputer, and we need to think about higher level languages. And so I actually thought about this a few years ago, looked around, and were particularly attracted to the ChaRM++ group at University of Illinois. So this is a C++ based parallel runtime system. The key object are these parallel objects that can be globally addressable. And so instead of doing MPI sends, you're doing asynchronous method invocation on these objects. And that's a little higher level of abstraction, a little more natural way to program. The magic comes in their runtime system, which actually places those objects on actual processors, and by doing so can manage scheduling, overlapping communication with computation. Load balancing can be done by moving these objects around, minimizing communication, and you can use the same system to do things like checkpointing and fault tolerance. And so we essentially ported our SPH code over into the ChaRM++ system, essentially a rewrite. And we call our new code ChaNGa for the ChaRM Embodied Gravity Solver. And we've unleashed it with a number of physics modules in the past year, particularly the supernova feedback that I just talked about, crude radiative transfer that interacts with our star formation. Michael has just added supermassive black holes, which are also important for galaxy morphology. And again, we've optimized these star formation parameters to match stellar populations in the local universe. So the remarkable thing is that this, it's a tree code that we've managed to scale out to 500,000 cores on blue waters. This is only 12 billion and 24 billion particles, getting nearly around 95% parallel efficiency. This is the easy case. This is a uniform distribution of particles. So load balancing isn't an issue here. If you look at a real simulated distribution of dark matter, this is what it looks like, not so uniform. ChaNGa, again, showed a picture much like this before. The difference with this picture is that a Milky Way-sized galaxy, well, this cluster up here is 2 or 3 Milky Ways in size and contains hundreds of millions of particles. The entire simulation is 24 billion particles. This is a distribution of the dark matter as it would look today, highly clustered. You're just seeing a slice with around 1 billion particles on the screen here. So the point here, very highly clustered distribution of matter if you're talking about these merely 25 megaparsec scales of the universe. So how do we address load balancing that? And that's where the CHARM came in well in addressing that imbalance. And then there's also multi-stepping challenges. That is, some particles we only want to calculate the forces every once in a while, and so the load shifts drastically as we go from large time steps to small time steps, and there are these fixed costs which the CHARM++ people helped us mitigate. Again, to visualize what's going on with the load, the colors aren't great here. This is a simulation, but each point here is not a particle, it's a virtual processor. Okay, so it's basically the centroid of a virtual processor, and the color is the load, computational load on that virtual processor. And so you notice this cluster up here, not only are there a lot of particles or virtual processors there, each processor has a higher load because it has a lot more gravitational interactions. And so this is sort of the CHARM++ view of the system. It can then map those virtual processors onto real processors, and now I've colored them by the actual processor it's been mapped onto, and we use this ORB tree to do that. And just the point that this horizontal division is so high up at the cube gives you an idea of how much more load is up here than there is down here. But with that, essentially that clustered Z=0 particle distribution on blue waters, now only 2 billion particles, we are able to scale out to 100,000 cores, only 80% parallel efficiency. But again, this is due to, from my perspective, the magic of the CHARM++ load balancing system. So that's how we address those challenges. We've done a couple science runs. The one I want to talk about a little bit we call the Vulcan. It's the same 25 megaparsec volume that we want to run, but it's only 1/10 the mass resolution that we really need. But it's essentially a pathfinding simulation so we can see how things are working. Forces not as good as we want, but it's still a 5 terabyte data set. The kinds of, oh, got to show the movie. I did have a mouse there, there it is. This gives you a little idea. Actually, this is only a 1/27th of the volume. I'm doing an MRI scan, just showing you what's happening with the gas as you go through the volume. And you'll see that around the galaxies, you will have these outflows coming out of them. So there's a lot of rich structure in that 25 megaparsec volume. So doing some analysis, here's what are the sizes and the luminosities of the galaxies that we find in this volume, and how do they compare with Hubble Space Telescope? Well, our results are the black histogram. Hubble Space Telescope data is the gray regions, and so we're quite pleased that we're matching. These are various redshifts, so this is the last snapshot, so the latest z equal 4, and going back earlier in time, obviously the data get worse, but we're still remarkably matching the luminosity. Again, brighter things are up here. But there's an interesting aspect to these luminosity functions, and that is that the slope at the faint end appears to be increasing as we go to higher redshift. Brian just talked about this. Maybe at very high redshift, this will stop happening. But at a slope of -2, that's actually divergent. That is, at that slope, most of the luminosity is coming out in the faint galaxies. And so this leads to the possibility that perhaps these faint galaxies are the things that can reionize the universe. However, as Tiziana pointed out, this will only happen if a significant fraction of the ionizing photons can actually get out of those galaxies. So Lauren has been looking at the escape fraction of these objects, and she finds that, particularly at the higher redshift, the escape fractions are pretty small. But keep in mind, these are still relatively low resolution simulations. If we look at sort of the absorption that an individual star formation region sees. So if I'm sitting on in a star-forming cloud and I look out in my galaxy, how much absorbing material do I see? This is the all-sky map. This is a relatively high escape fraction because there's a hole. Okay, and so clearly the more clumpy the medium, the more opportunities there are for holes and possibly higher escape fractions. So a motivation to go to the higher resolution simulations that we have planned. The other thing we should think about is adding black holes, because the black hole feedback can actually drive out some of that gas and perhaps lower the escape fractions. So we have been adding black holes. We try to let them form naturally as part of our star formation algorithm, but then they have to sink to the center of the galaxies, where that's where we find the supermassive black holes today. Unfortunately, well, we need the high resolution to follow that sinking process. There's a process called dynamical friction, which naturally makes heavy things sink to the bottom of potential wells. Here's an experiment where we're showing the sinking time. If you analytically calculate it, you get it should sink in a couple gigayears. And here's, following some simulations, here is essentially the resolution scale. So once it follows below the dotted line, it's at the center. So we've added a model which incorporates the dynamical friction, and we get the time scale correct. But if we don't have enough resolution, we get this light blue line. And essentially, the numerical noise starts preventing the black holes from sinking to the bottom of the potential well. So again, it's high resolution that we need to even get these black holes right. So what do the black holes do for us? So here's a simulation. The colors here are the metallicity of the gas. And I should point out to the non-astronomers that when we talk about metals, we're thinking about oxygen and neon. That would horrify your chemistry teacher. We also think about iron and nickel as metals, but anything heavier than helium, we call a metal. And so the red stuff is the very metal-rich gas. That is, those metals are being formed in supernova and ejected by the black hole feedback into the intergalactic medium. That's one of the more massive objects. Let's just zoom in on that to see how it goes. So this is the same simulation. The white spots are the forming black holes. They eventually sink to the center of these galaxies. Of course, this is all happening in a hierarchical merger scenario. And we can see, again, it's the supernova are forming the metals. And then as gas comes in and gets to the center of the galaxy, it's feeding the active galactic nuclei. That gives very energetic outflows from that central black hole and injects that metal-rich gas into the intergalactic medium. You get fresh supplies of low metallicity gas, continues to feed the star formation in this particular galaxy. The other thing the black hole will do as it drives out gas, it will lower the star formation rate. And our results show that depending on the growth of the black hole and the merger history, we can get a variety of morphology of galaxies that are coming out of these simulations. Some with ongoing star formation, some that are completely quenched and look like, nearly like modern elliptical galaxies. So again, let me emphasize that we need resolution to do this stuff. Even for the luminosity function, if you look closely, we had turnovers. This dashed line is our current resolution limit. And so we need to go another factor of 10 in mass resolution to see if these slopes continue down. Do these faint galaxies really contribute significant amounts of ionizing radiation? And so that's the plan for our next big run. We're actually testing out the black hole on a large simulation right now. It's at Redshift 6. And as soon as that's done, we'll do what we call our enterprise simulation, similar to what I've just shown you, but 10 times the mass resolution. If we get enough time, it would be nice to bring it to Redshift 0. We will include the black hole feedback. We will have star formation regulated by the formation of molecular hydrogen. And we will have half a petabyte of data to analyze. We expect some exciting results. Luminosity functions, plotted the wrong way, sorry. Mock observations in the HST flux bands with HST resolution. And we also hope to match up with the scaling laws, star formation rate, stellar mass, and metallicity relations that people are observing at a variety of redshifts. How much time?
I mean, that's just lunch after this, so I mean.
I could keep going. No, okay. So, well, all right, just a couple more slides, and I want to talk about that half a petabyte of data, okay? How do you handle that? And so we've been collaborating with our computer science database group at the University of Washington to see if we can load up, at this point, the terabyte data set into essentially a parallel database. And so they've designed this database called Miriam. And here's their bullet points. It can either be a cloud or on an HPC cluster. Right? Steve Scott last night pointed out the slowness of Hadoop or Spark, but it's similar type of paradigm, but it runs much faster. The idea is that through, say, a web browser or Python script, you talk to a web user interface that issue queries like you would on a database. It's sort of SQL plus stuff is the language. The computer scientists love to do this, right? This is their bread and butter, optimizing your queries, and then it sends out those queries for parallel execution. So this squiggly line could be a cloud, okay? Or it could be an HPC cluster, and you get essentially fast execution of your queries across a parallel data space where the actual data can sit on it could be a shared nothing cluster. That is, the data actually sits on the local disk of your cluster as it would be in a cloud. And so with this, we are able to, for example, examine the hierarchical merger trees, issuing queries and getting results pretty much interactively. So, so this is one of the ways we're planning to handle that tsunami of data that Blue Waters is going to produce for us. And so finally, just put up my acknowledgments. And again, hats off to the Blue Waters team, and of course the funding resources behind this. And thanks for your time.